Okay, so hello, and thank you to everyone who is taking the time to view this presentation. We're going to provide an overview of the Air Discharge Permit Application for Arbios Biotech and provide some background on Arbios and the Chuntoh Ghuna facility in Prince George, British Columbia. Before we get into the presentation, we just want to caution that this presentation is for informational and marketing purposes only, and does not replace independent professional judgment, advice, and due diligence. So please read the full disclaimer on this slide. So the Chuntoh Ghuna facility is in the traditional and unceded territory of the Lheidli First Nation, and we honor the Lheidli and are thankful and grateful that we can work together on the project, and also thank the nation for their welcome to the community. We are recording this presentation in June, which is National Indigenous History Month in Canada. And this is a great time for everyone to find out whose traditional territory you live and work within or travel to, and learn more about the history of Indigenous communities. I'm Tess and I work in external relations for Arbios Biotech, and joining me today is my colleague Ian Rose, who is the General Manager for Operations at Arbios. Also presenting today are two experts in their fields who have, along with their teams, conducted the studies and analysis that is required for an air discharge permit in British Columbia. Francis Rees is the environmental team leader for WSP in Canada, and Brian McEwen is the air quality meteorologist and practice leader in atmospheric sciences for Ausenco. And just to briefly touch on what we're covering today, Ian is going to provide a background to Arbios Biotech and the technology we use, before handing over to Francis, who will provide an overview of the best achievable technology assessment conducted for the Air Discharge Permit Application. And then Brian will provide a high-level overview of the air quality technical report and its findings. And lastly, we'll talk about next steps with the Air Discharge Permit and where to find out more information on the Chuntoh Ghuna facility and the permit application. So now I'll hand over to Ian Rose, General Manager of Operations for Arbios Biotech. Thank you, Ian.
Thanks, Tessa. Before we move into the best achievable technology assessment and air dispersion modeling results, I'll review some background content for the technology we are deploying, the process flow, the need for a change, as well as the size and scale of the facility we are building. Regardless of whether we are based in Prince George, elsewhere in British Columbia, or across the world, we are all experiencing the impact of a changing climate and realize that we need to reduce our reliance on fossil fuels and move to a sustainable, low-carbon future. While many industries are adopting new low-carbon technologies, some sectors, such as aviation and marine transportation, require drop-in, low-carbon solutions, as it will take decades before they replace their existing fleets. This is where Arbios can play an important role by producing a renewable bio-oil as we move to this lower carbon future. Arbios is a joint venture between Canfor and Licella. Canfor is a leader in the manufacturing of high-value, low-carbon forest products, and Licella is an Australian-based technology pioneer in the area of next-generation recycling and global leader in the development of their hydrothermal liquefaction technology called CAT-HTR. Arbios' plans are to demonstrate this first-of-a-kind technology in Prince George to reduce global carbon emissions. CAT-HTR stands for Catalytic Hydrothermal Reactor, which is an advanced hydrothermal liquefaction process and uses high-temperature water under high pressure to transform the low-value biomass into a high-quality, sustainable bio-oil, a direct substitute for fossil crude. It is important to understand that this is a conversion process and does not involve the burning of biomass. As part of our commitment to a circular, sustainable bioeconomy, we have been working in partnership with the Lheidli First Nation since the beginning of the project, starting with a site blessing before any preparatory work began. Arbios has also been working with the nation to protect the nation's values with respect to environmental interests and traditional and cultural uses. We are proud that the Kleklitene elders named our facility, calling it Chuntoh Ghuna, meaning the forest lives. We were able to celebrate this at a facility naming ceremony in August 2022. The size and scale of the facility is small when compared to typical industrial facilities in the region. The Chuntoh Ghuna facility is situated adjacent to the Camphor Intercon pulp mill on the northwest side of the mill off PG Pulp Mill Road. This location is beneficial for utilizing existing site infrastructure. Being situated in Prince George positions us close to the local sources of renewable biomass residues, and in British Columbia, we benefit from strong provincial policies that support the introduction of new low-carbon technologies. As previously mentioned, the size of the Arbios facility will be small and is modular in design. The site location will be close to reliable feedstock, which enables us to focus on lowering the carbon intensity. The first line will be used to demonstrate this technology at commercial scale, with very modest production rates of approximately 50,000 barrels of bio oil per year to start, and a scale up to 100,000 barrels per year, which is approximately 300 barrels of bio oil per day. This is small when compared to production rates of a typical refinery, which can almost be 40 times more. We'll be taking a conservative, phased approach, which will allow us to demonstrate the technology and realize efficiency improvements to reduce carbon intensity before scaling up to full production rates. This slide shows a simplified process flow diagram and is used as a basis of our discussion throughout the presentation. The process is divided into three main sections. The first section is the biomass storage and handling area. Here, there is a small biomass storage area, covered conveyors, screens, magnets, shredder, and a dryer. All of this equipment is focused to create a uniform quality feedstock. The second section uses small boilers to produce supercritical water at high temperature and pressure, which is then combined with the feedstock into the CAT HTR to convert this low-value biomass into a high-quality bio oil. Then, in the third section, the produced bio oil and residual water are separated and stored. For this stage of the project, this is where our process will end. The stored bio oil will then be transported off-site for refining or further upgrading to produce biofuels that can be used as a drop-in fuel for transportation. Here we see an aerial photo of the site location in an existing industrial area. To be specific, our facility is located to the west of Camphor's Intercon pulp mill, east of United Initiators, and to the south of the Tidewater refinery. And the reason for this presentation is to highlight that we are in the process of applying for an Air Discharge Permit with the BC Ministry of Environment and Climate Change Strategy. We submitted a preliminary application in March 2022 to initiate this application process. Since then, we have made a number of process improvements, specifically related to controlling dust emissions, which will be reviewed in the Best Achievable Technology Assessment. And as such, our final application will have an updated discharge factor form. To provide perspective for the presentations that follow, this slide shows the facility layout with 9 air discharge locations, as well as 4 miscellaneous and non-point source discharges. These locations are identified by the red circles on the facility layout. It is worth noting that the process areas and core technology occupy a small section of the site, even with the completion of the planned expansion. At this point, I'll pass the presentation over to Francis, who will discuss the Best Achievable Technology Assessment that WSP has performed for Arbios. Thanks, Francis.
Thank you, Ian. I'm Francis Rees, and I manage WSP Canada's Air Quality and OHS group in BC and the Yukon. I'm going to provide a high-level walkthrough of the Best Achievable Technology, or BAT assessment that my team conducted for the Arbios facility. A BAT assessment is sometimes required by the BC Ministry of Environment and Climate Change Strategy as a component of waste discharge permit applications. BAT assessments look at the operation of a given facility and identify discharges of contaminants to the environment. For each discharge, the assessment reviews control technologies that have been proven in commercial application and whose risks are known. The assessment then determines which technology is best suited to meet waste discharge standards for protection of the environment and human health. The assessments focus on 4 key assessment criteria: the feasibility of a given technology, given the design criteria and constraints of the facility; long-term reliability of the technology under a range of operating conditions; effectiveness of a technology at controlling contaminant levels; and cost effectiveness of the technology in terms of both cost per unit reduction and cost relative to overall facility capital and operating costs. In performing the BAT assessments, we look at applications of control technology in other similar types of facilities, and we review what types of technologies are required in the permitting of similar facilities in BC. BAT assessments are often paired with air dispersion modeling assessments, which focus on predicting the impacts of discharges on the receiving environment. Brian will speak about the dispersion assessment conducted for the Arbios facility later on. To facilitate the BAT assessment, Arbios provided WSP with design information for their facility, along with extensive information about the processes that they have undertaken to select the various technologies employed at the facility. This slide provides a summary of a number of measures that have been taken to minimize emissions at the facility. First, with respect to biomass drying at the facility, Arbios has selected a low-temperature belt dryer. This technology facilitates the recycling of heat created from the CAT HTR process, thus enabling the drying of biomass without the use of any fuel combustion. In addition, the use of low-temperature belt dryer also minimizes emissions of volatile organic compounds that may be produced from drying of biomass. For operations that within the facility that handle dry biomass, Arbios have specified a dust collection system which connects to each of the operations and then routes any collected dust to a bag filter dust collector. Some process gases will be produced in the conversion of biomass into bio-oil. These gases are being routed to an enclosed combustor to ensure that they are treated and eliminated prior to discharge to the atmosphere. Handling the biomass as it is received at the facility and as it is introduced into the process is going to be conducted with covered storage for the biomass as it arrives at the facility, and in addition, covered conveyors as the biomass is handled and introduced into the drying process. So in assessing the technologies which were reviewed on the previous slide, and assessing other operations within the facility, WSP undertook the assessment process discussed earlier, looking at the feasibility, reliability, effectiveness, and cost effectiveness of each control technology. In approaching the handling of fugitive dust within the facility, WSP determined that rather than handling emissions of fugitive dust with a particular technology, instead, it is best practice to manage these emissions via a fugitive dust management plan, which includes a range of monitoring activities, triggers, and actions to manage dust emissions. With respect to the handling of dried biomass, as mentioned on the previous slide, Arbios plan to employ a collection system for the dust from dry biomass. The best achievable technology for handling of such dry biomass particulate emissions is a bag filter dust collector, and the typical operating parameter required for best achievable technology is 20 milligrams per cubic meter or better in terms of discharge concentration. For the biomass dryers themselves, best achievable technology was determined to be low temperature belt dryer, as previously indicated. In addition to minimizing emissions of particulate matter, this type of dryer also minimizes combustion emissions because no combustion of biomass or other fuel such as natural gas is required to perform the drying. And in addition, low temperatures of this drying approach will also minimize emissions of volatile organic compounds. For the supercritical water boilers, which supply the supercritical water required in the CAD HTR process, a number of technical constraints and the high costs associated with alternative treatment solutions resulted in the determination of best achievable technology for these boilers being the use of the manufacturer's standard burners together with good combustion practices. Due to this determination, the use of NOx emissions control technologies such as selective catalytic reduction were not selected as best achievable technology due to their high cost and concerns related to reliability and feasibility of such technologies. The best achievable technology for the vacuum column heater, which is part of the separation process after the CAD HTR, is the use of manufacturer's standard low NOx burners together with good combustion practices. For handling of vapors from the process, it was determined that based on the BC Oil and Gas Commission flaring and venting guideline, as well as industry practices for handling of process vapors, best achievable technology was determined to be the use of an enclosed combustor with the important parameter that it must achieve greater than 99% destruction of the waste gases being combusted. Leaks from process fittings and flanges and valves within the facility will be managed not by one particular technology, but similar to fugitive dust, should be managed via a preventative maintenance program, which includes leak detection and repair of equipment that contains gases or high pressure liquids. Finally, based on standard industry practice, best achievable technology for the control of emissions from wastewater treatment is the use of an anaerobic wastewater reactor with all off gases from the reactor treated in the vapor combustor, as previously discussed. That concludes my summary of the best achievable technology assessment. Now, I would like to pass the presentation over to Brian McEwen to discuss the air quality technical report.
Thank you, Francis. My name is Brian McEwen, and I led a technical team from Asenco to do an air quality assessment for the Chuntoh Ghuna facility. Now, this assessment is twofold, really. One is to assess the emissions expected from the facility, and we've already heard a lot about that from Francis. Not just what the emission rates are, but also how they're released into the atmosphere, and then an atmospheric dispersion model. So this essentially is an approved government model that represents the weather and also the release of contaminants into the air and how they transport and disperse. So air dispersion modeling is what I'll be talking about mostly. Now, the model requires representation of the Chuntoh Ghuna facility emissions by themselves, and then addition of what's called a baseline or background air quality. And this background air quality is taken from existing monitoring data. In this case, it's the Plaza 400 monitoring station in Prince George. And as you can see here, this background was established with 2016 data for particulate, PM10, PM2.5. The PM stands for particulate matter of 10 microns in diameter and 2.5 microns in diameter, respectively. And then 3 years of data for NO2 and SO2, so nitrogen dioxide, sulfur dioxide. The reason why there is more data available to establish background for NO2 and SO2 is because there were no problems with the monitoring equipment during those 3 years, whereas there were some difficulties with particulate monitoring after 2016. So we'll keep coming back to this, baseline or background concentration that we add to the modeling, and when these baselines were developed. In particular, there is a clear understanding that there have been changes in the Prince George airshed to industrial emissions recently, and so we do expect that existing air quality currently would be better than characterized in these past years. Also, I should point out that there's a lot of technical detail in the study that we completed. So I will highlight certain parts of our study, but there is a full air quality technical report that can be found online at arbiostech.com. So the atmospheric dispersion modeling study that we did is meant to be a worst case simulation of what could occur in the region, right? So it isn't a simulation of actual emissions or typical emissions. It's a simulation of maximum emissions from the facility at levels that are never actually expected to be met or exceeded. And of course, all players involved work to ensure that those levels are never actually experienced at the facility. So it's a cautious approach, and it identifies potential air quality concentrations that may not be realized. So inputs to the model start with meteorology, right? It has to simulate the atmosphere, and then also the emissions from the Chuntoh Ghuna facility. And these inputs are maximum flows and concentrations that are based on guarantees from the equipment vendors, with additional levels added just to make sure that they're conservative or higher than will be experienced. I also want to point out that the simulation of air quality in terms of particulate is fairly straightforward, in that the emissions from the sources at Chuntoh Ghuna are largely free to move and disperse in the atmosphere without chemical transformation. This isn't the case with nitrogen dioxide. The nitrogen oxide emissions are released primarily as NO, or nitrogen monoxide, and converted over time to nitrogen dioxide. So this chemical transformation process has to be simulated as well in the modeling that we do. And it adds a level of conservatism that leads to higher predictions than we think would be experienced. So I'll talk a little bit about that as well. Now, all of the sources that we characterize have emission rates that are higher than actual, and in particular, the emission rates of fugitive sources. So these are sources that are not defined through a stack, and we have fugitive sources from the handling of biomass. The way they're characterized in the model and the methods that we employ are developed in consultation with the Ministry of Environment. There's strict guidance in terms of how this modeling is done, and also a review process between the consulting group and the Ministry of Environment to make sure that it's understood and accepted the methods that would be employed. Now, the methods that were employed for fugitive dust assume a dry biomass pile, which will not actually be the case. The biomass pile used will likely be quite wet during most of the time. And also the handling procedures are through covered conveyors, which wasn't understood at the beginning, or that this work was done, the air quality assessment was done. So it was simulated with open conveyors. So we do think that the way fugitive dust is represented in the model is much higher than will actually occur. And in most situations, we think the emissions from fugitive dust, due to proper environmental management at the facility, will be near zero. I also want to point out, again, that there has been changes in industrial emissions in Prince George, which means there actually is significant reductions in particulate and NOx that is not represented in the model. So here's a portrayal of changes in the airshed over the last couple of years, what has changed since we have done our determination of baseline or background air quality. And we have additional emissions from Tidewater renewable diesel, and they're quite minor, as you can see. We have significant reductions in both particulate and NOx emissions from Pacific Bioenergy pellet plant, which closed down recently, and also the pulp mill line that closed down at PG Pulp. So the net effect of emissions that have recent changes in emissions are a decrease of almost 12 grams per second of particulate and over 8 grams per second of NOx. So these reductions are quite a bit higher than the contributions from the Chuntoh Ghuna facility. And so we'll talk a little bit about that as well, what effect we'd expect that to have in reality versus what the modeling implies. So the emissions themselves were carefully calculated and characterized, and you can see a summary of these permitted emissions here. For each contaminant that was addressed in the assessment, you can see TSP for total suspended particulate, PM10 for particulate matter of 10 microns and less, PM2.5 of particulate matter of 2.5 microns and less, as well as nitrogen oxides, sulfur, and sulfur dioxide. So if we focus on PM2.5, you can see that the biomass dryers are the largest source of PM2.5, and they're characterized with an emission rate of 0.41 gram per second each. Now, these emissions are established as levels not to be exceeded. We also identified in the technical report of what the expected emission rates would be, or typical emission rates, based on testing of similar dryers that are active elsewhere in the province. So this sort of typifies what we see as differences in typical emissions versus maximum emissions. And in this case, the typical emissions from the biomass dryers are expected to be quite a bit less, and total PM2.5 emissions maybe about half of what we see here for the worst case or maximum permit level emission rates. So these are the emission rates that are put into the model, and the model simulates the advection, the movement of contaminants and dispersion of contaminants, leading to predictions of air quality concentrations. This is a quick graphical reminder of changes, or sorry, the contribution of the Chuntoh Ghuna facility emissions in regard to other industry, and commercial, and residential emissions in the airshed. Now, the emission sources are well understood in Prince George, in part because there's been a multi-year study conducted by the PG Air Group and facilitated and contributed to by UNBC. And these emissions have been modeled as well. Now, the modeling that the university has done has not been a worst case or regulatory model like we've conducted here, but rather a modeling of the typical or the actual emissions. So there are differences in what the UNBC model has predicted in the past years to what our modeling here would imply. And notably that the UNBC model predicts lower concentrations because it does not use maximum permit level, never to be exceeded emission rates. What's important to note here is that the contribution from the Chuntoh Ghuna facility at the maximum rates are about 2% of total emissions or less. And these are at the maximum emission rates. For typical emission rates, we'd be looking at more like half these numbers. So again, back to PM2.5, the typical PM2.5 emissions are expected to represent about 1% of the total PM2.5 emissions in the airshed. Here is a table of modeling results from a 3-year simulation that was completed. So again, this is a regulatory atmospheric dispersion model. It was run for 3 years, and the worst case impacts during the 3 years were identified. The predictions are separated to impacts of the Chuntoh Ghuna facility on its own, and that's what you can see in the top rows here without background. And then once the baseline or background concentrations for monitoring data are added. Now, the way that air quality is assessed is the model predictions are compared to government objectives. So the far right of this table, you'll see AAQO, which stands for Ambient Air Quality Objective. So the maximum model prediction is compared to these concentrations here. And to give an example, TSP, the first AAQO you see is 120. That is 120 micrograms per cubic meter. So this is a concentration in air, and the model predicts a worst case concentration in air. The background levels that are added, and you'll see this coming up in our report and what will refer to as we go through the contaminants, that the contribution of the facility, it tends to be rather low, but when the background is added, there can be predicted exceedances. And this is because the background in some cases is quite high with respect to the objective. So if we look at PM10 in particular, the established background is based on the 98th percentile of measured data from Plaza 400. So this is a data point that's pulled out of the monitoring data directly as a 98th percentile or value that would only be expected to be experienced 2% of the time. So it's quite high and it's quite close to the objective. So not surprisingly, if we take the model results from Chuntoh Ghuna itself, their contribution, and add the background, we can get modeled exceedances. If we look at PM 2.5, the background value is still relatively high, but it's lower on a percentage basis. It's 84% of the objective. So to quickly sum up here, we have some graphs to show you what this looks like spatially. The predictions without background are identified at what's called MPOI in the table, or maximum point of impingement. And we do see that for all particulate forms here, TSP, PM10, PM2.5, the model predicts there can be an exceedance at the MPOI, which is right at the facility fence line. Now, the facility itself is in industrial zoned lands, so we don't expect that this is a problem on its own, because the public does not frequent this area. What's more important in the modeling is to identify predicted concentrations at what are called sensitive receptors. And so the nearest sensitive receptors that could be impacted are identified in this table: senior care facility, school, hospital, nearest residence, and also the Claytley 10A traditional use areas. So we've got predictions at these locations too. And if we run through the table, you can see that the predictions from the Chuntoh Ghuna facility alone are considerably lower than the objectives. Now, once we move down the table, adding background, you can see that there can be exceedances. So PM10 in particular, you see that the model, when adding background, exceeds at the MPOI and also exceeds at the sensitive receptors. And so in the assessment that we complete, we do identify that there are modeled exceedances, but these are largely caused by the high background levels in Prince George. Here we have graphical representation of PM10 concentrations. In this case, it's 24-hour averaging period. And if you remember, the government objective for 24-hour PM10 is 50 micrograms per cubic meter. So the red line, as shown here, is that 50 micrograms per cubic meter. And so everything inside that contour is where the model predicts that there may be an exceedance. So at the worst case emission rates persisting for a full 3 years, the highest maximum prediction at any time of the year is depicted here within that red contour, which extends about 200 meters from the facility. If we look further away from that contour, we can see that the Chuntoh Ghuna contributions to air quality quickly fall off, and the last contour shown is 10 micrograms per cubic meter. So the impacts from the emissions almost entirely fall within the industrial zoned lands by the facility. And once we get further afield into residential areas, the impacts are quite low. For example, by Plaza 400, the predictions are on the order of several micrograms per cubic meter. So as a result, with our assessment of PM10, we identify that there can be exceedances of the objectives within 200 meters of the facility, and this is due to the Chuntoh Ghuna emissions alone. But the ambient air quality objectives do not typically apply to industrial facility areas or industrial zoned lands. So public exposure to these emissions and air quality concentrations is expected to be minimal. When we add background, and again, the background PM10 is relatively high for Prince George at 49 micrograms per cubic meter. There can be exceedances, and these exceedances do occur at distances away from the facility. However, the facility contributions at sensitive receptors are low relative to the background air quality. Similar to PM10, this figure here is a depiction of the maximum predicted PM2.5 concentrations from the Chuntoh Ghuna facility. So similar to PM10, we see that the model predicts there may be an exceedance of the government objective, in this case, which is 25 micrograms per cubic meter, within about 200 meters of the facility. The actual maximum prediction is right on the fence line, not far from the dryers. The impact, the air quality impact from these emissions falls off quickly, as with PM10, and you can see that they drop to about 5 micrograms per cubic meter within about 400 or 500 meters. And once you get further afield, the contribution drops to about 1 or 2 microgram per cubic meter. So fairly low. In this case, even when we add the background or baseline concentrations, we have no exceedances of government objectives at any sensitive receptor locations. So the concluding statements in terms of assessment of PM 2.5 are that the facility contributions at sensitive receptors are low relative to background air quality, and there's no cumulative exceedances at sensitive receptor locations. This figure shows the NO2, so the predicted NO2 concentrations from the modeling. And as I mentioned earlier, the modeling of NO2 is a little more complicated because we have to deal with the chemical conversion of emitted nitrogen monoxide to nitrogen dioxide. This is a depiction of air quality concentrations due to both the Chuntoh Ghuna contributions and background. And this is because the Chuntoh Ghuna emissions on their own, we have no predicted exceedances at any location. So only when we add the background do we see that the model predicts there can be exceedances of the government objective. In this case, it's the 1 hour objective. There are no exceedances of the annual objective. So for the 1 hour objective, the model predicts there can be exceedances near the facility on those industrial zoned lands, but also across the water on the hillside near the correctional facility. No exceedances are predicted at sensitive receptors. So in reality, as we mentioned, this method of simulating the chemical conversion of NO to NO2, we expect that it's conservative. The model also tells us that the relatively high predictions only occur during poor dispersion conditions, typically viewed as inversion conditions in Prince George. So inversion conditions are when there's a layer of warm air above the surface, which inhibits the movement of air contaminants out of the airshed. So this essentially what we're seeing here is a worst case impact of NO2 with the background contributions and occurring during inversion conditions, which are expected about 2 to 3% of the time. And so these conditions occur often in the winter and usually in the late evening or early morning hours of the day. This is a representation of the predicted concentrations of the Chuntoh Ghuna facility of PM 2.5 on top. This is hourly PM 2.5 and hourly NO2 on the bottom. And you can see as well what was actually measured during the 3-year simulation period. So this is a comparison of air quality impacts, maximum air quality impacts from Chuntoh Ghuna over what was measured on these same days at Plaza 400. So in this case, you can see that there's a small contribution from Chuntoh Ghuna at many hours of the year, and it doesn't change. It doesn't change too much. So it's a contribution of about 1 to 2 micrograms per cubic meter, and it remains quite low compared to what is actually measured at Plaza 400. If we shift now to NO2, we don't see contribution at all hours of the 3 years here. And this is because the contribution from Chuntoh Ghuna in terms of NO2 is very low at most hours of the year, except when these inversion conditions persist. And that's why you see few sort of red lines, but when they do exist, they can be higher. Now, as I mentioned, we expect that the contribution from Chuntoh Ghuna facility is overestimated by about a factor of 2. So we don't expect these contributions to materialize, but it's important to understand that the significant contributions that could occur from the facility emissions are quite rare. In conclusion, then, we are able to make a confident statement that the facility is not expected to adversely affect air quality in Prince George. So it has to be understood that the assessment we did is a worst case assessment, where we look at emission rates from the facility that are not typical. They're emission rates that are never expected to be met or exceeded. And we're also adding a worst case contribution from all other industrial sources, industrial, commercial, and residential sources in the airshed. And we've seen that already there have been significant reductions in emissions of particulate and NOx, and these reductions are considerably higher in magnitude than the contributions expected from Chuntoh Ghuna. So We also looked at other air contaminants that I didn't address today, SO2 being a significant one. And the reason I didn't talk about these is because the modeling clearly shows that the risk of exceedance of any air quality objectives is very, very low. The model predicted no exceedances of any objectives of SO2, and it was the same for other air contaminants as well, notably carbon monoxide. So we are comfortable at saying that no adverse air quality in Prince George is expected with the operation of the Chuntoh Ghuna facility. Thank you. Back to you, Tessa.
So thank you, Brian. Highlighting the next steps in the Air Discharge Permit Application, there is a 30-day notification period on the permit application. And after the notification period, we will finalize our submission to the British Columbia Ministry of Environment and Climate Change Strategy, their Industrial Waste Authorization Division. The ministry will then review the application. So if you have any comments or questions on the application, please visit our website where you can download the air quality technical report that Brian talked about today, as well as find out more about Arbios Biotech and the Chuntoh Ghuna facility. You can also email any questions to us directly on info@arbiosbiotech.com. I'm just going to close this presentation today by saying thanks to Ian, Francis, and Brian for your presentations, and thank you to the viewers for taking the time to watch our presentation today. Thank you so much. Goodbye.